developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
My name is Simon Laflamme, and I'm the PI on the project. Under this project, we're concerned by the problem of estimating the condition of high-rate systems in real time. High-rate systems are engineering systems that experience very drastic and rapid changes in dynamics. For example, a hypersonic object going through a target. Our research team is developing software enabling real-time state estimation for these systems, which will empower real-time decision capabilities in the sub-millisecond realm.
One of the interesting challenges to overcome in tuning our machine learning algorithm was to find a way to extract information about underlying dynamics in real time while maintaining lean mathematical formulating to ensure computational efficiency. We have been able to do such by incorporating advances in algebraic topologies. With this technique, measurements are transferred into dynamic point clouds, and we extract topological features from these point clouds to inform the machine learning representation on the current state of the system.
One of our goals is to demonstrate our algorithm on a microcontroller. We are currently working on implementing basic functions in Arduino to understand the complexity in integrating our code, and our microcontroller can interact with measurements collected online.
Since starting this project, we have designed a machine learning architecture capable of learning high-rate dynamics in real time. Our software can run in a sub-millisecond range and can therefore be used to address our high-rate state estimation challenge. Thanks to our funding, we have progressed towards tuning the algorithm targeting realistic applications. At this stage, we have parameterized the machine learning architecture for forecasting time series of dynamic systems undergoing strong impacts. And we also started to investigate the implementation of our code on hardware.
One interesting discovery that we made in the last 6 months is that we can dramatically improve computational speed by creating a new set of features inspired by computational topology. We call our technique FastTDA. In FastTDA, we try to attract geometrical features from a topological space in real time. For example, the location and size of ellipses that can be used to partly fit local point clouds. We have established a formal procedure to do so and plan to validate our novel method by benchmarking against our current method based on traditional algebraic topology. If successful, FastTDA could accelerate field implementation of our high-rate state estimation software.
We made great progress over the last 6 months of research. We have developed software architecture capable of extracting time series features on the fly for complex dynamic systems, and finally it was possible to significantly improve algorithmic performance by implementing feature extraction strategy based on topological data analysis. We've also established a path to implementing software on hardware that includes performance metrics and validation procedures. One of our group students, Metrid, spent 1 week at the AFRL at Eglin and worked with Dr. Dodson's group, along with other students from the University of South Carolina that work on electronics hardware for high-rate systems. Through this collaboration, we were able to understand opportunities and limitations in implementing deep learning algorithms on microchips and establish a path to implement full software functionalities.
Hello, my name is Jacob Dodson. I work at the Air Force Research Laboratory, Munitions Directorate at Eglin Air Force Base, Florida. I wanted to talk to a couple of the key significant attributes of the program, the implementation of high-rate state estimation algorithms being executed by Iowa State University, and really the significance to the Air Force. So this piece of research that is looking to deploy these algorithms onto hardware is part of a larger framework that allows us to do high-rate structural health monitoring on key Air Force systems during high-speed flight and during target engagement, in which we want to monitor key attributes and systems of our structure to ensure that it's still operating its full capability. If we detect that sudden impacts or sudden changes in our boundary conditions lead to degrading functions, we would like to change the way we're operating our system to still get the maximum benefit. So the algorithms allow for us to detect sudden changes in our structures and these uncertain and high amplitude loading events so that we can then use that for high speed decision making to really maximize the benefit of our Air Force structures.